Okay, next section. We're going to go back to talking about pizza. So we used this example before. Here's a pizza recipe. Now we're going to say, well, what if we have 4 crusts and 10 cups of cheese and 15 ounces of tomato sauce? How many whole pizzas could we make? I heard 3, 5, 6, and 1. 3. Okay, so we can figure this out, but you can think about it. Okay, so how'd you come up with 3?
15 ounces.
15 ounces, right? So I'm going to show you what we were doing in our heads. We were taking each ingredient, 4 crusts, 10 cups of cheese, 15 ounces of sauce. And mentally, okay, I have not lost my mind. No, actually I did, but that was a long time ago. I haven't recently lost my mind. The iPad keeps doing this funny thing where it messes up what I'm writing.
Where'd you find it?
Find what?
Mine.
I never did find it.
I was hoping.
Of all the things I've lost, I miss my mind the most. So what we're doing mentally is we're figuring out how many pizzas we could make from each of these ingredients, whether you recognize that that's what you're doing or not. So there it goes again. We can make 1 pizza for every crust, right? So we could make 4 pizzas if we had enough of the other stuff, right? From the cheese, it takes, oh my goodness. We get 1 pizza for every 2 cups of cheese. So that would give us 5 pizzas. Close enough. The sauce, it takes 5 ounces, and so we can make 3 pizzas. Yep, the universe is out to get me today, it's official. So why can't we make 5 pizzas? There's not enough sauce. We run out of an ingredient, right? This happens a lot. Day before yesterday, I had to make cupcakes because yesterday was my daughter's 11th birthday. So I went to the store and bought 2 cake mixes because there's 32 children, and so 1 cake mix isn't enough. I had lots of oil. I had lots of water from the faucet. I had lots of eggs, actually. I had enough eggs. I did check. But I couldn't make more than 48 cupcakes because I didn't have more cake mix, right? And so there's a limiting reactant. It's very unusual when you're cooking that you have exactly the right amount of everything. Like, it would have been really weird if I had had exactly 6 eggs in the refrigerator and exactly 1 cup of oil left in the whole house and only 2 cups of water available, right? That would just be bizarre for that to happen. It just doesn't happen that way. It doesn't happen when we're doing chemical reactions either. Generally, there's 1 reactant that gets used up, and we call it the limiting reactant because it limits how much product we can make. Just like here, we have a limiting ingredient, the tomato sauce. We run out of it, everything stops. Here's a picture demonstration of this. So the 4 crusts could make 4 pizzas. The cheese could make 5. The sauce could make 3. So what we did is we figured out how much product we could make from each of the ingredients, and then the smallest one is the one that we can actually make. And the one that produces that smallest is called the limiting reactant. Limiting reactant is the reactant that makes the least amount of product. The maximum amount of pizzas we can make which is the amount from the limiting reactant, is called the theoretical yield. It's theoretical because things rarely go perfectly in chemical reactions. There's a lot of reasons why you might not get all of it. Okay, I don't think there's anything else I have to say there. So in chemical reactions, usually one of the reactants is going to get used up. That's the limiting reactant. It gets completely consumed, the reaction stops. Then we've got leftover stuff. Those are called excess reactants. Okay? Now, when we're making pizza, I haven't had too many pizza accidents, but we've had some pancake accidents. You're making pizza. What if you burned one? You know, you've got enough stuff to make 3 pizzas, but you got this phone call that distracted you and you didn't hear the timer and one of them is like black, right? How many pizzas did you actually make? 2. That's your actual yield. In theory, you should have been able to make 3. So there's an actual yield and a theoretical yield. And to express our efficiency, we use percent yield. Percent yield is just the actual over the theoretical. So percent yield equals the actual yield. And in a problem in the book or on an exam, we have to tell you what the actual yield is. It's divided by the theoretical yield. I call him Theo. The theoretical yield times 100.
We did this not that long ago, didn't we?
We did percent yield for, no, we did percent error and we did percent recovery. We use percents a lot. It's always the part over the whole times 100. So yeah, it does seem familiar. Oh, so these are summary slides. Limiting reactant is the one that gets used up, limits how much product. The excess reactants are the ones that are not the limiting reactants. Theoretical yield is the amount that can be made based on the amount of limiting reactant. The theoretical yield is something that you calculate using stoichiometry. The actual yield, if you're doing the experiment, it's the stuff you actually get that you weigh at the end. If you're doing a problem, they have to give it to you in the problem. And here's the equation for percent yield. Let's look at our little methane combustion reaction. Here we've got methane reacting with oxygen to form CO2 and water. And the equation tells us that if we have 1 molecule of methane, it's going to react with 2 molecules of oxygen. So we can't have, if we only had 1 molecule of oxygen, the reaction can't go forward, right? Just like if you only had 2 ounces of pizza sauce, you can't make the pizza because you don't have enough sauce. So if we had 5 molecules of methane and 8 molecules of oxygen, what could happen? I really like the green pointer and I keep messing it up. Well, first we're going to calculate the number of CO2 molecules from the 5 methane. So this is the same thing we did with the pizza. So 5 methane molecules, this ratio comes from the chemical equation. 1 CO2 for every methane. And we find that we could make 5 CO2 molecules, provided there's plenty of oxygen. We do...
Oh, I'm sorry. That was the right side.
And then it said we had 8 molecules of oxygen. So 8 molecules of oxygen, the ratio was 1 CO2 for every 2 oxygens. That would allow us to make 4 CO2 molecules. 4 CO2s is smaller than 5, and so this is the least amount of product, and that tells us that oxygen is the limiting reactant.
Can you go back to the actual equation?
This one?
Yeah.
So we get 1 CO2 for 2 oxygens, we get 1 CO2 for every 1 methane.
Okay.
So there's 1 carbon that's unmatched.
Well, there's 1 carbon in here, and it shows up in there.
That's right.
We need 2 moles of oxygen because there's some oxygen also going over to the water. And you can't just say, well, I'll just give my 2 oxygens to the carbon and let the hydrogens fend for themselves. The reaction won't happen. You could possibly have another type of reaction happen, but it's not going to be this one. Yes?
Why did you use CO2 for this?
Well, the question is, what's the limiting reactant? So they're not actually asking us for a yield. We have to look at one of the products.
Okay.
You could look at either product.
Okay.
And since we've been talking about CO2, they just chose to do CO2.
Gotcha.
So this is how your book recommends that you do these problems. And if this works for you, that's fine. I'm going to change it a little on you. They say take the mass of A, convert to moles of A, convert to moles of your product, and stop there. Then do another calculation, mass of B to moles of B to moles of product, and stop there. And then compare those two and identify which is smaller. Whichever one is smaller, you're going to bring down here and convert to mass, and that's going to be your theoretical yield. That's fine. That works. But I think it's kind of confusing for students, and I don't think it's really actually any faster. And so what I prefer to do is go all the way to mass of product for both.
Mass to moles, moles to grams.
Grams to moles to moles to grams. You're going to end up with 2 masses. Choose the smaller one, and that's your answer. You're done. So that's my method, and that's what I'm going to do in my examples. Any questions? So a limiting reactant problem, you're going to do the same process, grams to moles to grams, but you're going to have to do it more than once. Let's do an example. Ammonia can be synthesized by this reaction. What is the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? Well, let's write those numbers down. 5.22 kilograms of hydrogen, 31.5 kilograms of nitrogen. They're asking for theoretical yield of ammonia in kilograms. So we want ammonia in kilograms. We can identify this as a limiting reactant problem because they're giving us masses of more than one reactant. The previous examples that we did before this section would say, provided plenty of oxygen, provided plenty of the other, right? And so there were no limiting reactants. So we're going to do 2 calculations. How do you want to deal with the kilo part? Do what I did before? Okay. So we're gonna do grams to moles to grams for 2 reactants. So the first one is going to be the hydrogen. You don't have to do the hydrogen first, but it comes first, and so I just kind of like to do it first. I'm just going to make this kilo blue to kind of point him out that we're not going to cancel him out. We're just going to leave him there hanging. Kilograms of hydrogen. So I'm ignoring the kilo, and I'm just going grams to moles to grams. So to moles of H2, to moles of ammonia in H3, and then grams of ammonia. Down here, moles of NH3. Down here, moles of H2. Down here, grams of H2. The grams of H2 cancels the grams of H2. The kilo didn't cancel. So when I do this, I'm going to end up with kilograms of NH3. What goes in the middle here? How many moles of NH3?
2.
2. And how many moles of H2? 3. And then over here, I've got the molar mass of hydrogen. That's 2.016. 2 times the mass of hydrogen. And then over here, I need the molar mass of ammonia, which is 17.034. 1 nitrogen times 3 hydrogens. So 5.22 divided by 2.016 times 2 divided by 3 times 17.034 equals. How many significant figures should my answer have? 3. 29.4. Any questions? So that's 1. We need to do it again. So I'm gonna use a different color here, just for grams.
What is that? 29 point?
29.4. It's not the best 9. Having troubles writing today. So 31.5 kilograms. I'm going to do the same thing with the kilo there. N2. 31.5 kilograms of N2. And grams to moles to moles to grams. Moles of NO2, N2s. 2 moles of ammonia. 2 grams of ammonia. Down here I've got moles of ammonia. Those are going to cancel, and I've got moles of N2. Those are going to cancel. And then down here I've got grams of N2. This cancels grams of N2. It does not cancel the kilo. The mole ratio comes from the balanced chemical equation. 2 moles of NH3. How many moles of nitrogen? 1. Look at this one. Grams of ammonia, moles of ammonia. That's the same. We don't have to go calculate another molar mass. That last term is just the same. And then I need the mass of nitrogen. That's N2. So that's 28.02. We've got 31.5 divided by 28.02 times 2 times 17.034. This will also have 3 sig figs. And so this is going to be 38.3. The kilo is still in there. Grams of NH3. Sorry. NH3.
The first one is the limiting.
The first one is limiting. So the theoretical yield is always the smallest one. And if you have a hard time remembering that, think about pizza. When you run out of one ingredient, you stop, right? When we run out of hydrogen, the reaction stops. And so it's always the smaller amount of product. That is the theoretical yield. About the only time I see handwritten stuff from you guys is on lab reports. But sometimes I'll have a paper that maybe you had to solve this problem, and this is exactly what is seen. You know, they show me. I'm like, okay, that's great, really good work. But it's wrong because you didn't choose an answer. You have to pick an answer. right? So you have to indicate your answer somehow. Any questions? Let's do another one. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams of Fe. Determine the limiting reactant, theoretical yield, and percent yield. Well, let's take the numbers and write them under the balanced chemical equation. Seems to be working okay. So 167 grams of iron, Fe2O3, 85.8 grams of carbon monoxide, and it says it produces 72.3 grams of iron. They want the limiting reactant. Well, limiting reactant we find by calculating theoretical yield, right? Doing two calculations and finding out which is the smaller. Then they want the theoretical yield. So the two calculations would give the theoretical yield. Is this the theoretical yield? Did they just hand it to us? No, this is the actual yield. They're saying they reacted this with this and it produces this much. To do the percent yield, we need the actual yield and the theoretical yield. They have to give you the actual yield. So this guy right here, this is the actual yield. And so we need to calculate the theoretical yield, question mark, grams of iron. Grams to moles to moles to grams, twice.
So what are we finding first?
We are going to find the mass of iron that can be produced using, it's not the, 167 grams of Fe2O3. And we're going to go grams to moles to grams of iron. And then we're going to do the similar calculation for mass of CO and find mass of iron. These are both going to mass of the same product. The smaller one is our theoretical yield.
And we're doing it to iron because it's asking, or because it says it produces the 72.3 grams of.
Right, we're finding mass of iron instead of mass of carbon dioxide because the problem indicates that that's what we're interested in.
So you can basically just leave the 3 CO2.
The 3 CO2 is just, it's formed and
Okay.
we don't really care about it. Yeah. Okay, so 167 grams of that, 2 moles. Moles of Fe2O3, 2 moles of iron. They seem to be having fun in the next lab. 2 grams of Fe. Units go down here. Fe2O3. And down here is grams of Fe2O3. Iron, 55.85. Bless you. 2 irons and 3 oxygens. 2 times 55.85 plus 3 times 16. 159.7 grams per mole. $159.7 grams of Fe2O3 per mole of Fe2O3. Mole ratio comes from the equation. You get 2 moles of iron for every 1 mole of Fe2O3. And then the mass of iron
55.
is just 55.85. No calculating because that's an element. 167 divided by 159.7 times 2 times 55.85 equals. If this was a final answer, we would have 3 sig figs here, 116. It's not our final answer, so I'm going to carry 2 extras, and the units are grams of iron. I'm going to have to use my theoretical yield in the percent yield calculation.
So now we have to do the 85.
Now we have to do the CO. So similar calculation. 85.8 grams of carbon monoxide. We're going to go to moles, carbon monoxide, and moles of iron, and grams of iron, and then the units in here, moles of iron down there, moles of carbon monoxide down there, and grams of carbon monoxide. This last term is exactly the same, although it's all squished and small.
It's just iron either way, so no calculations.
Pardon me?
It's just iron either way, so no.
It's just iron, yeah. You're always going to the same product, and so the last conversion factor is always going to be the same when you're doing a limiting reactant problem. Here, again, we're looking at the equation. 2 irons, and how many carbon monoxides? 3. This is at 3. And then we need the molar mass of carbon monoxide, which would be carbon, 12.01, plus oxygen, so 28.01. $85.8 divided by 28.01 times 2 divided by 3 times 55.85. This one would also have 4 sig figs. I'm going to carry 2 extras, 0.05. 114.05 grams of iron. What's the theoretical yield? The smaller one. So this is the theoretical yield. You should label it somehow. What's the limiting reactant?
CO.
CO. It's the one that made this. Just go back. There it is, CO. So carbon monoxide, that's the limiting reactant. And then we need percent yield. Just making some space here. So percent yield is actual yield over theoretical. The actual was given to us, 72.3 grams. The theoretical is 114.05 grams. And then we have to multiply by 100 to make that a percentage. 72.3 divided by 114. Try that again. 72.3 divided by 114.05 times 100. How many sig figs should that have? 3. So 63.4%.
And you did 3 sig figs because of the 72.
I did 3 sig figs because of the 72.3 and also because of the 114.05. I underlined this 4 because this number came from this mass, which only had 3 significant figures. Any questions?
So we can write the theoretical yield at 114, and that's true, right?
Yes. I kept the extras because I knew I was going to use it in this calculation. If you're just, reporting it, yeah, I'd say 114. This is, kind of a marginal yield. If you're this iron company owner, you're going to say, hey guys, what can we do to get this yield up, right? We're wasting a bunch of our ore. We're not getting the iron out of it. What can we do to increase the yield? And that's the sort of thing that chemical engineers are very interested in. It's very cool.